all this work that we've done so far with these binomial coefficients and this n choose r and all this stuff has led us towards this thing called the binomial theorem. And really what this is it might look intimidating, but this is going to actually give us a simpler way to generate these binomial coefficients rather than having to spend all the legwork expanding things as we've done so far. And the binomial theorem states that if I have some expansion of a plus b to some n power, that's just given as n or a to the n power plus n choose 1 to the a minus 1 times b plus dot 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 plus some n choose r times a to the n minus r power times b to the r power plus ba 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 all the way down to b to the n. This might look really complex and confusing, but we'll kind of match it up with some actual numbers that you've seen before in just a second. And we'd say that n choose r is the binomial coefficient of the term a to the n minus r times b to the r. And r can equal any number from 0 all the way up to n. Again, all these letters are being thrown at you, but you've seen what this means, and we're just kind of representing this algebraically. So let's take a look at a plus b to the 5th power, the expansion there. So we know this expansion at this point. We've done this before using Pascal's triangle. And let's kind of piece that or map that together with this general a plus b to the n power. The first term is always a to the n. In this case, if this is a 5th power expansion, my first term is a to the 5th power. The next term is n choose 1. And if I have something to the 5th power, my expansion here, this 5 comes from 5 choose 1, which we found before. And 5 choose 1 is 5. 10 is given as 5 choose 2. And so on and so forth. In general, n choose r gives us whatever the binomial coefficient is. If this is the third term in a binomial coefficient, this would be 5 choose 2. The second term in a binomial coefficient is 5 choose 1, and so on and so forth. And these powers, this whole a to the n minus r times b to the r thing, that's what we've talked about before, how these powers always sum up to whatever the power of the expansion is. So we've got 3 plus 2, we've got 2 plus 3, we've got 1 plus 4, always sums to be 5. And then also, if you can think about this n minus r and r piece, the 5 choose 2, if the r is the bottom number here, that should correspond with the exponent on that second half of my term here. And then this exponent will always be whatever the power is, 5 minus whatever your r is, or in this case, r is 2. So again, this looks kind of like jarring because we have all kinds of symbols floating around all over the place, but we've been dealing with this stuff the whole time. We just haven't given it this symbolic notation. So in general, the general term, or the r plus 1th term, is given by this expression or equation here. Really, at the end of the day, this is all that you need to take away from this binomial theorem. You can generate any term by using this n choose r times a to the n minus r times b to the r. This is the one that you want to commit to memory out of any of the things we've seen so far. And we'll get some practice on how to use these things. One thing that we can add to this is we can use sigma notation to pack the entire binomial expansion for any polynomial or any binomial expansion to any power using the sigma notation. In math, we love to take these massive complex ideas and boil them down to generalizations. And that's what we've done with sigma notation. We could say that the expansion of a plus b to the n power is given by the summation, here's our sigma notation, from r equals 0 to n of n choose r times a to the n minus r times b to the r. If we were to expand this, we would get this up here. So in this example, we want to write down the first 3 and last 3 terms of the following expansion. So here is my expansion. Here's a, here is b, and it's to the 12th power. So this is where we don't want to use Pascal's triangle. We want to use that general equation. The r plus 1th term is going to be given as n choose r times a to the n minus r times b to the r power. And when we're looking for the first 3 terms, what we're really looking for is, I'm going to list this as the first term t1, second term will be t2, and the third term will be t3. And what I'd like to do is let's keep track of what the r values are. Over off to the side, I'm just going to write the r values. since this is an equation for the r plus 1th term, the r is going to actually be 0 for the first term, the r is going to be 1 for the second term, the r is going to be 2 for the third term. When I look from my last 3 terms, one thing that we have to remember is that if this expansion is to the 12th power, my last 3 terms will actually end with a 13th term. And so I have T13, T12, and T11 to find here. And maybe what I'll do is I'll jot down the R values on the side here. So I have an R value of 10, an R value of 11, and an R value of 12. All right, so now I want to just find all these things by plugging stuff into my equation, my T sub R plus 1. So when I'm looking for the first term, that's going to be given as, well, in general, if I have n choose, if I have n choose 0, that will equal 1. Or if I have n choose n, that will equal 1. And this basically are the ones that are always on the outside of your Pascal's triangle. That first number is always 1, that last number is always 1. So what we're going to do is that we're actually going to leave out n choose 0, and we're going to leave out n choose n, since those are already 1s. So normally for the first term, I would write n choose 0, since r is 0, but I'm just going to leave that out as a 1. So what I do have is I have the a, which is 2x, to the n minus r power, or 12 minus r power. So this is to the 12th power. And I'm going to move this down a little bit. There we go. So this isn't part of the b here. So then the first term is 2x to the 12th power. And I'm not even going to write the b to the 0 power in there, since that is equal to 1 anyways. The second term is going to be when r is equal to 1. So this will be 12 choose 1 times 2x to the 11th power times b, which is 1 over x, to the first power. My third term will be 12 choose 2 times 2x to the 10th power times 1 over x to the second power. So that takes care of my first 3 terms. And then my last 3 terms, I'm going to do the same thing as I did before. So when r is equal to 10, this is going to be 12 choose 10 times a, which is 2x, to the 12 minus 10 power, so this is to the second power, times 1 over x to the 10th power. My 12th term will be 12 choose 11 times 2x to the first power times 1 over x to the 11th power. And then my 13th term will be 12 choose 12, and again that's equal to 1, so I'm going to leave that out. So this is going to be 2x, and actually I'm going to leave the 2x out as well, because that'll be 2x to the 0 power. So instead I'll just write 1 over x to the 12th power. And I can actually combine this and write it in a more elegant way, and just say that the expansion of this for the first 3 and last 3 terms is 2x to the 12th plus 12 choose 1 times 2x to the 11th times 1 over x plus 12 choose 2 times 2x to the 10th times 1 over x squared plus dot 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 plus 1 over x to the 12th power. All right, so I got a little tight there. So give yourself some room when you're writing out these expansions. One thing that I did notice here as I was writing this actually should be a 2x to the 10th power. I should not have written that parenthesis there, so my apologies. This is 2x, that whole thing, to the 10th power. So that was a whole lot of work. The thing that kind of is killer about these problems is just it's a lot of plugging things in, it's a lot of writing, and a lot of room to make mistakes. So watch your steps carefully. Rewatch this if you need to, but why don't you try the next example where we are writing down the first 3 terms and the last 3 terms. Be careful finding your R values. Use that equation that we had before, and give this one a shot. Pause the video, and good luck, and may the math be with you. All right, so here is my answer for this one. Again, I used that same equation from before. I identified my A, I identified my B, and you carry that out to get the following expansion in an unsimplified and kind of an ugly but still good form.